What's up, everybody? It's Dan from SageMathTutoring.com, and here we have a video that pertains to solving systems of equations and systems of inequalities. So what I'm going to do here is the red circled problems, okay? So looking at problem number 5, use substitution to solve each system of equations. If the system does not have exactly one solution, state whether it has no solution or infinitely many solutions. Okay, so when it comes to substitution, um, you're going to want to have one of the equations be such that one of the variables is by itself. So, for example, we have this y by itself right here, but that's actually good. That's sort of conducive to the process. The fact that this y is by itself and then y equals 3x. So, therefore, we could say for sure that anytime we see a y, we could hypothetically replace it with a 3x. And that's exactly the um, truth that you're taking advantage of when it comes to substitution. So y equals 3x, but for the next equation, I'm going to write x plus not y, but x plus 3x equals 4. And then we can solve this equation here now that the y had been replaced with a 3x. So that's going to become 4x equals 4. Let's divide both sides by 4. You would have x equals 1. Uh, we have solved at least half of the system by understanding that x equals 1. And at that point, you're just going to plug that 1 back into x. Now, you could plug 1 in for x either in the top equation or the bottom equation, actually, but this top equation is going to be a little bit easier. So if we were to plug in x equals 1 there, well, that would become y equals 3 times 1, and that, of course, is equal to 3. So y is equal to 3, so therefore the solution to this particular system of equations is 1 comma 3, because x is 1 and y is 3. Okay, looking at, let's see, problem number 11 now. Determine the best method to solve each system of equations, then solve the system. Well, once again, we have an equation such that one of the variables is by itself right here, which means that substitution is going to be a pretty good way to go. So if we were to um, rewrite this bottom one, only instead of 3x plus y equals 11, we're going to write 3 times the entire quantity of 2y minus 1 plus y. That's going to equal 11. So we've done nothing more than replacing x with 2y minus 1 because we know that x equals 2y minus 1. So therefore, after distributing, we would have 6y minus 3 plus y equals 11. Combining like terms gives us 7y minus 3 equals 11. Adding 3 to both sides would give us 7y equals 14. Dividing both sides by 7 would give us y equals 2. Now we have discovered that y is equal to 2, which means we could plug 2 into that equation right there. So I'll rewrite it down here. It's going to be x equals 2 times, not y, but 2. We can actually replace that y with a 2. And then we have minus 1. That's going to be 4 minus 1, which is 3. So the solution to this particular system of equations is 3 comma 2. Now, once again, I chose to use substitution for this particular system because this particular system featured an equation that already had an isolated variable. And whenever the variable is isolated in this way, it actually makes it very easy to substitute because we know that anytime we see x, we can replace it with a 2y minus 1, and that's exactly what we did down here. Okay, looking at problem number 12 now. So we have that. It's probably the case that elimination would be the best method because if we could just turn this negative y into a positive y, well, then we could add the top equation to the bottom equation and it would be a negative y plus y, which would cancel out the y. So my thought is let's make that happen by multiplying the bottom equation by negative 1. And as a result, that literally just changes the sign of everything. You're going to have a negative 3x plus y equals, and we can say negative 13. Now, in the name of not being distracted, I'm actually going to get rid of the old equation that we had before, because at the end of the day, we're just going to work with these equations, the first equation and the updated equation. So if I was to add the top equation to the bottom equation, 5x plus negative 3x is clearly 2x. The y's will cancel out, which is exactly what we wanted. And we have, of course, the 17 minus 13, which is just a 4. Dividing both sides by 2 gives me x equals 2. So that's one of the coordinates of the point of intersection. Now, since x equals 2, what that means is we can take this top equation, put 2 in for x. So I'm going to write 5 times 2 minus y equals 17. That's obviously 10 minus y equals 17. Subtracting 10 from both sides gives me negative y equals 7. Dividing both sides by negative 1 gives me y equals negative 7. So that's the y coordinate of the point of intersection. Okay, so looking at this problem, we have 13. The sum of two numbers is 17 and their difference is 29. What are the two numbers? So we could call one of the numbers x and we could call the other number y. There's no reason why not. And it is the case that the sum of these two numbers is 17. So we know right out the gate that x plus y is going to be equal to 17. And since the difference is 29, we know that we can say x minus y equals 29. Now, could I have said y minus x equals 29? Yes, I could have, but it actually doesn't matter. Okay, we have some number that happens to be greater than the other. In this case, we're going to assume that x is the larger of the two numbers. So at this point, let's see. So it does seem like elimination would be a good idea, because if we were to add this top equation to the bottom equation, the positive y would cancel with the negative y. So let's go ahead and add this bottom equation. We'll bring it down here. So the x plus x is, of course, going to be 2x. And then you have the y plus negative y. This just cancels out. And then on the right-hand side of the equal sign, we have 17 plus 29. So that's going to be 30 plus 16, which happens to be 46. So then dividing both sides by 2 gives us 23. Now, since it's the case that x is equal to 23, we can plug in 23 in for x in either of these equations. I'm going to say let's go ahead and work with the top equation. So rather than writing x plus y equals 17, I'm going to write 23 plus y equals 17. Solving for y by subtracting 23 from both sides would give us negative 6. So y happens to be negative 6. X happens to be positive 23. Y happens to be negative 6. So that's the answer to that one. Okay, looking at problem number 15 now. 235 in nickels and dimes. If she has 33 coins in all, find the number of nickels and dimes. So we could say that n represents the number of nickels, not the value necessarily, but the number of nickels. So if I have 10 nickels in my pocket, well, n would be 10 in that case. We're looking at dimes as well. So d would equal the number of dimes. Now, let's actually focus on the second piece of information first. We know that this person has 33 coins in all, so we know that n plus d, the amount of nickels plus the amount of dimes, is going to equal 33. Now, when it comes to these money system of equations problems, it's often the case that you need some equation representing like the quantity of coins, and then you're going to need another equation that pertains to the actual monetary value of what you have. Okay, so in this case, it's $2.35. Well, that's going to be 235 cents. You could think of it that way. Let's sort of just imagine everything's in terms of cents, because at the end of the day, it's going to be 10 cents for every dime that this person has, plus 5 cents times the amount of nickels that this person has. Okay. So these are two perfectly valid equations that we can use to solve the system, right? Now, at this point, I'm going to say that substitution is a pretty good way to go because I could immediately isolate this n by subtracting d from both sides, and we would have 33 minus d. Now, the point is, when it comes to that, is that I have isolated one of the variables, which makes substitution um, easy to do. So I'm going to rewrite the top equation as 10d plus 5 times. Now I could say n, but now I'm going to replace the n with a 33 minus d. So I'll write that here, 33 minus d. And that equals the 235 cents. Now, of course, we would have to distribute. So we would have 10d plus 5 times 30 is 150 plus 15 is 165 minus 5d equals 235. And then at that point, combining like terms, we would have 5d plus 165 equals 235. Subtracting 165 from both sides, we give a 0. 70, and I think that's actually it, right? That would be it. So dividing both sides by 5 would give us 14, I believe. So that's 50 plus 20. Yes. So apparently we have 14 dimes. Now, since it's the case that we have 14 dimes, we, of course, need to figure out how many nickels we have, and that would be a matter of using really any of the two original equations, but I kind of like using this updated version of the second equation because it's like n equals 35 minus d. That's going to be very easy to work with. It's going to be n equals 35 minus, well, I could say d, but we already know what d is. D is 14, so I'm going to write 14. Now 35 minus 14 is 21. So therefore, we have 21 nickels and 14 dimes. Okay, looking at problem number 16. Solve the system of inequalities by graphing. So the way to go with these is to graph the lines. Now, before you graph the line, you may want to ask yourself, is it going to be a dotted line or a solid line? And you know it's going to be a solid line when there's an underline underneath the inequality symbol, and you know it's going to be a dotted line when there's not an underline underneath the inequality symbol. Otherwise, you can kind of graph these in a normal fashion. So we have y equals x plus 2, or y is greater than x plus 2. So the y-intercept is clearly 2, so we could sort of write that here. And then the slope is 1 over 1, so you go up 1 over 1, up 1 over 1, up 1 over 1, right? Just like that. And maybe I could do a couple down here. So it's really just that simple. And it will be a dotted line, though. So we're looking at a dotted line that goes like that. So hopefully that makes sense. Dotted line. Now, the way that I teach this is a little different perhaps than the way that many teachers teach it in school, in that if you want to know which region to shade, well, you basically pay attention to the y right here. And you ask yourself, if the y is greater than x plus 2, that means you're going to be shading above the line. If the y is less than or equal to the expression over here, they're going to be shading below the line. Now, clearly y is greater, so in this case, we will be shading above the line. Okay, so that's the deal with that. Now, as it pertains to the second equation, we have y is less than or equal to negative 2x minus 1. Well, we know that there's a negative 1 as the y-intercept down here. It's negative 2 over 1 as the slope, so we go down 2 over 1, down 2 over 1, down 2 over 1, and so on, right? And it would really be up 2 to the left 1 here, up 2 to the left 1, up 2 to the left 1. Now, in this case, it's going to be a solid line, right? Because there's an underline underneath the inequality symbol. So we could go ahead and graph that nice solid line like that. Okay. Now, with regards to shading, we would be shading below the line that we just drew. So we're going to be shading everything below the line. Now, what the problem is specifically taking interest in is the double shaded region, which is this green region. Now, it is the case that this green region is the answer to this problem, okay? The green region features all of the points, the XY coordinate points, that would satisfy both of these inequalities, such that if you plug in X and Y, it would indeed be true that Y is greater than X plus 2. And if you plugged in X and Y here, it would indeed be true that Y is less than or equal to negative 2X minus 1. Okay, looking at problem number 17, sort of a similar situation, right? Let's get this ready. So, when it comes to the first one, we know they're both going to be solid lines, first of all, because there's an underline underneath the inequality symbol. So this one has that y-intercept of 2. We could write that right here. And then the slope is 1/4, so that means we go up 1 over 4, right? Up 1 over 4, down 1 to the left 4 over here, down 1 to the left 4 over here, and therefore drawing a nice solid line between these would be that. With regards to shading, y is less than all of that, so therefore we are shading underneath, okay? We are shading underneath. Okay, fantastic. Now with regards to the second inequality, does say that y is greater than or equal to, I guess that's 2x. Whoever had this review sheet wrote a +0 there, because it is the case that if it's y is greater than or equal to 2x, it is the case that the y-intercept would be 0. So we can sort of draw our point at that y-intercept of 0. Now the slope happens to be 2 over 1, so we're going up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, and so on, down 2 to the left 1, down 2 to the left 1, down 2 to the left 1, and then drawing a line, solid line by the way, between these points would give us something that looks like that. And with regards to shading, we would be shading above that line, so we can do that right here, shading above the line, shading above the line. Okay, because y is greater than or equal to 2x. So looking at the double shaded region, obviously this green area would be the double shaded region, right? So that is that one. Okay, problem number 18. To qualify for a certain needs-based scholarship, a student must get a score of at least 75. Okay, before we dive in, just know that the phrase at least means greater than or equal to. We could also say that no less than, the phrase no less than, that also means greater than or equal to. If you hear a word problem say at most, something is at most something, that means less than or equal to. And if you hear a word problem say no more than, then that would also be less than or equal to, okay? So we are dealing with a word problem that's using the phrase at least. So it is the case that we're going to be imagining a greater than or equal to scenario. All right, and to be clear, the phrase at least is right here. All right, so to qualify for a certain need-based scholarship, a student must get a score of at least 75 on a qualifications test. In addition, the student's family must make less than $48,000 a year. Define the variables, write a system of inequalities to represent the situation, and name one possible solution. So the score, we can say, is X, right? And the money, the salary, we could say, is Y. Now, according to the word problem, the score, the X in this case, must be at least 75. So I already said that means it's going to be greater than or equal to 75, right? And the salary, which is Y, has to be literally less than $40,000 a year. Okay. Now, these are lines, actually, that we could graph, believe it or not. We could graph these lines. They happen to be special lines in that they are vertical and horizontal lines. So, for example, the X is greater than or equal to 75. That's a vertical line, okay? And the Y is less than 40,000. Then that's a horizontal line. Uh, I am seeing, however, that it's going to be annoying to graph this because it's like, I suppose um, we could call this 100,000 right here, 100,000, and therefore this right here would be 40,000. Okay, we could do it that way. With regards to X being greater than or equal to 75, that's kind of tricky. We could call this 80 right here, and therefore 75 would be like right there. Okay, so kind of weird, kind of annoying. We could call this 100, and basically just goes up by 10, 10, 20, 30, and so on. So 75 would be right here. Okay. Now, X is greater than or equal to 75. Well, that means that we would have a solid line, a solid vertical line at 75. And since X is greater than or equal to, that means that we're going to be to the right of that line. So that's this. Okay. And by the way, for my student watching at home, do you have to graph these? Not necessarily. Okay. In fact, you can kind of just use logic with regards to naming one possible solution. Just pick a value of X that's greater than 75 and a value of Y that's less than 40,000. It's really just as simple as that. But I did want to sort of illustrate the fact, literally, that you can draw a graph here. So with regards to the Y is less than 40,000, let's imagine this is 100,000. This is 40,000 right there. So that would be a dotted line though, right? So we're not allowed to actually be 40,000. That salary cannot actually be 40,000. It has to be a salary that is less than 40,000. So we're shading therefore everything below that line. Shading everything below that line. So what that means is our solution set is in the green area, right? We're in the green area. Now, let's just pick any old point. Let's say 90 right there, 90 as a possible score. And we could say that right there is 10,000 right there, okay, as a possible salary. So we could say salary, um, Y equals salary, and in this case, one possible solution would be 10,000 as a possible salary, and then the X, which we already said, is going to be equal to the score, potential score that you could earn. Well, in this case, according to this point, that score we're going to say is 90. So that's one possible solution to this particular system of inequalities. All right, so hopefully that's helpful for my student watching this at home. Good luck And hopefully this was helpful for everyone watching, and I will talk to you all later. Bye.